Okay, so welcome to our N3AS seminar. Today we are very pleased to have Professor Salvatore Vitale from MIT. He will be talking about next generation gravitational wave experiments. Over to you.
Hi, thank you very much. Let me start my watch so I have an idea of time. All right, thank you very much for having me. Though virtually, it's really nice to be here and tell you about the gravitational waves, astrophysics, the next generation. The title is very actually explicative of what I'm going to talk about. All right, so let's get started. As you probably figured out already from the graphic on the title slide, this talk is going to be mostly about black holes. The main reason why I like them is that they are one of the most mysterious and fascinating and extreme objects in the universe, and yet they are ubiquitous. Every massive star leaves behind a black hole. There are supermassive black holes at the center of galaxies. And in fact, because most stars in the universe are in binary system, there should also be a lot of black holes in binary system like this one. And it would be nice to answer some key scientific questions about these objects. For example, when did these black holes form throughout cosmic history? What role did they play in the formation of structure in the universe, possibly through repeated mergers? What are their masses and how fast can they rotate around their axis? Do they pair with neutron stars with the same frequency with which they pair with black holes? And do they remember anything, or can they teach us anything about the stars that they come from? Or even more simply, how many of those objects are there in the universe? And now these are questions which are very hard to address using traditional methods based on mostly X-ray astronomy, so on light. The main reason, of course, is that black holes don't emit light. And so when we observe them with telescopes, what we're really observing, it's a disk of matter that they are accreting, like as shown here in this artist representation. And now this is great, and this has allowed to learn a lot about black holes over the last several decades. However, it also comes with two main shortcomings. One is that, again, what we are really measuring are properties of the disk, and from that, inferring properties of the black holes, which come with potential biases. And the other is that this approach based on photons only really works for stellar mass black hole in our galaxy. So the sample is limited, a few tens of black holes, with a few more discovered every year. And so wouldn't it be great to have another ways of studying black holes? And of course, gravitational waves do provide this alternative and clean way of studying compact objects, in particular black holes. All right, so this talk is going to be mostly about, I wouldn't even call it a talk. Anupam told me that we really want a vigorous discussion and Q&A at the end. So more than a talk, I would call this, me proposing a few things worth thinking about and talking about later with you. So mostly we're going to talk about next generation detectors, but of course I would be remiss if I didn't tell you what's happening today, since we have detectors taking data, right now. And I only got basically one slide about that to tell you where LIGO, Virgo, and the other detectors are. So we are now just a bit above 8 years since the discovery of gravitational waves in 2015. And we have detected 88 binary mergers. Those are the ones that we as the LIGO Virgo collaboration published. Then on top of these 88, there are 81 candidates mergers that have been made public from the latest observing run, which we call O4. So this plot on the right here shows on the x-axis observing time in non-consecutive day at the bottom. If you want to have the calendar period, you can find it on the top x-axis. O1 to O4A is how we have called our observing runs. And the vertical axis gives you the cumulative number of detections. And this makes the point that, when we started, this was a trickle of, black holes every few months. And now we are in this region where we add, for a new candidate every few days, pretty much every day or two, which is really very impressive. And now of these 160 some mergers, most are binary black holes. We have so far published 2 neutron star binary detections, including a very famous one from 2017, and 4 systems of 1 neutron star merging with a black hole. Now, which was also particularly remarkable because those systems, those heterogeneous mergers, have never been seen with the telescopes. Now, this is great. However, one thing I want to stress, which is in common about all of the sources LIGO and Virgo are detecting now, is that those are relatively local sources, where I put local in quotes because that definition depends on who you ask to. And for black holes near what we know now is the peak of the mass function around 10 solar masses, well, LIGO can see them up to redshift of maybe 1. So that's good. It's, of course, way more than our galaxy, but it's still a small scale compared to cosmological distances. Now, things will get a bit better over the next few years because LIGO and Virgo will increase their sensitivity over the next 5 to 10 years. So I'm showing this on this basically table here on the right, which maybe you have seen some early version of. The x-axis as the calendar year, and these blocks tells you observing run and sensitivity associated with LIGO, Virgo, and CAGRA. So right now we are, and again, I'm assuming you can still see my pointer, we are in this gray gap, which is a commissioning break between the first and second part of 04 in here. And we are at the sensitivity of 150 megaparsec for detecting neutron star binaries. Virgo and CAGRA are a bit behind because of a series of issues that they have had. Anyhow, the point I'm making is that as we progress, for example, with the 5th observing run, which is planned to start in 2027, the sensitivity is a bit better. Here you see again the number for neutron stars. So we should be able to see them up to 300-ish megaparsec. For black hole, of course, that horizon is much farther. In fact, I like to think about it in terms of redshift. And so for advanced LIGO in 05, we're going to be able to see black holes, again, at the peak of the mass function at around redshift of order of unity. And there is even a plan, something called a sharp, to happen after 05, so somewhere in the early 2030s, that will push the redshift horizon for black hole up to redshift of order of 2, which again starts being cosmologically very interesting. However, you always have to look forward in science at what happens next. And the truth is that once you reach this point, this A-sharp design, you are basically in a situation where you have saturated everything you can do in the current LIGO and Virgo facility. Basically, you're limited by the size of your detector. So no matter how smart you are, you cannot go much better than this. And so that's why we are already designing the next generation of gravitational-wave detectors. This is like in 2 bullet points are the main points I'm going to go back to. Those are targeting operations in the mid-2030s. So we have a 10 years time scale. Once online, they would detect between 100,000 to 1 million sources every year. Some of those will have incredibly high signal-to-noise ratios. I'm going to go back to some of these points as I go. By the way, I should also say, feel free to ask questions throughout, even though I try to be sure to leave ample time at the end. All right, so what are these next generation detectors? There are 2 main designs being proposed. One by our friends in Europe is called the Einstein telescope. Now, this, if you want, is the one that will look most different than what we have now. In such is that it will be triangularly shaped. Here you see an artist rendering. Though the legs will be 10 kilometers of the triangle. And as you see from, again, the cartoon, it will be underground. The reason for that is that you want to beat seismic and Newtonian noise. So your sensitivity can go all the way down to a few hertz as opposed to 20 hertz that we have today. Now, the Einstein telescope design is quite mature. Our friend in Europe have been thinking about this for over 10 years. I think their first science book was in 2011 or something like this. Recently, they got very good news. They have been included in the European Strategic Forum for Research Infrastructure. That's a mouthful, but basically means that they are nearly guaranteed that they will get money. They are really on the fast lane for happening. They have even identified a few promising sites, the main two being in the Netherlands and in Italy. Okay, so that's the design that our friends in Europe are following. Here in the US, we are working on a design called Cosmic Explorer. Cosmic Explorer, as you see here in this artist impression, will look more like LIGO. In fact, it looks like a bigger version of LIGO, L-shaped, but with arms of 40 and or 20 kilometers in length. Now, work it's happening toward Cosmic Explorer. In 2018, the NSF founded a group of people, including us here at MIT, to work and write an horizon study that would explore design options and scientific potential for ground-based next-generation detectors in the US. So we wrote this horizon study. Here you see the archive link above the figure here if you want to look at it. More recently, meaning last year, a group of people have been awarded $9 million to start an MIT-led conceptual design study, which in NSF lingo is when things start to get serious. And in particular, my group focus within this effort has been in developing the science case for Cosmic Explorer, at least part of it. All right, we have also, I should say, put together some formal structure to shepherd all the activities and give them a coherent path forward. So the Cosmic Explorer project has been formed in 2021 and includes an order of 40 people. And we also have a Cosmic Explorer consortium, which includes over 500 scientists around the world that you are more than welcome to join. It does not come at any FTE commitment. And we basically organize calls with scientific talks and on either the instrument or the observational science and so on and so forth. And we're also organizing a second a Cosmic Explorer symposium. This is going to be online in a month and a bit. You can go if you're interested in register. There is an Indico webpage in here. I'm one of the organizers. If you have any questions, feel free to ask me. So part of what the Cosmic Explorer project is doing, of course, is, again, come together with a consistent and coherent view for what the path toward the Cosmic Explorer looks like. And here, I'm showing a possible timeline. That's what we're working with right now. We are somewhere in here, and we are indeed, as I mentioned, working on the design study, which is this pink block, while also starting to understand where this kind of detector could be built in the US. We are trying to follow, a path different than what has been, done for other astrophysical hardware, in such that we are from the very beginning folded in interaction with the communities, including Native Americans, in our selection strategy. All right, and yeah, I don't want to go through all of these blocks. The idea is that if everything goes well with funding, we may be taking data in the mid-2030s. Over the last year or two, a lot of things have happened which were positive for the path toward Cosmic Explorer. Two of them have been that the Astro Decadal was published, and it came with a very strong endorsement for Cosmic Explorer. I'm not going to read the quote. It's here if you want to read it later, but basically, the community has strongly endorsed a growth in sensitivity of roughly a factor of 10, which is what Cosmic Explorer would guarantee, calling essential to development of gravitational-wave astrophysics. Similar good words came from the DOE HEP side in the SNOMAS report from the Cosmic Frontiers group, which again highlights the importance of gravitational-wave observatory for the HEP community, and in particular, a detector with sensitivity a factor of 10 better than LIGO, which is Cosmic Explorer, as I'm gonna document in a bit. All right, so that's all great. Even more importantly, early in 2023, so a year ago pretty much, the NSF has charged a committee to, in quote, assess and recommend a set of concepts for next generation observatory in the US. So basically, the NSF has realized that the time is now pretty much to start working seriously on what comes next. So this committee has been put together and asked the community for white papers to send your idea for a concept of a next generation detector. And we in the Cosmic Explorer project submitted a 40+ pages white paper, also with input from the consortium. Here you see the cover page and the archival link if you want to read it. This is public. It's an interesting reading. It's not particularly long or technical. And now we are waiting. This NSF committee will make their report public either by or at the April APS. The chair of the committee, who is Vicky Calogera, has a talk about this at the APS. Unfortunately, she not give anything away in the abstract. There's no abstract. All right. So having told you a bit about the structure and where we are and where we think the path is from the organizational side, let me switch toward the physics and what we can do. So let me start with a plot that may be familiar to some of you. This is a plot that shows the sensitivity of a gravitational wave detector. On the x-axis, you have frequency, so we are in the audio band. And on the vertical axis, we have noise, so lower it's better in these plots. So O3 is the sensitivity that LIGO had in the third observing run. A+, it's basically at this point a synonym for O5, so the next observing run, the one starting in a couple of years. A# is what I told you earlier as being the best you can potentially do in a facility that is 4 kilometers in size, such as LIGO. Now, the other curves, let me go through them one by one. You see CE 20 and 40 curves. Those are Cosmic Explorer, depending on whether you built it of 20 kilometers in length or 40. The reason why we are considering both is because a 40-kilometer detector gives you more sensitivity overall, but a 20-kilometer detector, so these dark green curves, give you better sensitivity in the kilohertz region, which I'm showing you with my mouse, and that's where we expect a lot of information from post-merger signals from neutron star binaries to come. And so that's why we are still considering both of these options, because if we decide we may want to focus on neutron star science, it may be interesting to have a 20-kilometer detector around. And by the way, this kind of trade-off is part of what this NSF committee could comment on. And then in pink, you see the curve for the Einstein telescope detector in Europe. Because they are underground, they can do better at low frequency. So you can see that their low frequency sensitivity is lower than the Cosmic Explorer one. And the dashed line here, it's the best you can do. I see your hands up. I'm going to pause in a second. Is the best you can do in the Cosmic Explorer facility, possibly in the 2040s, but I'm not going to talk about it. Yes, Susan, go ahead.
Oh, thank you. I just wanted to ask why there is a kink in the sensitivity curve and Cosmic Explorer in the 40-kilometer arm at 3 kilohertz.
Yes.
What is that feature? What is driving that?
So what is driving that is basically what my friends that work on the instrument call the free spectral range of the detector. And basically what that means is that when your detector is long enough, it starts to become comparable to the wavelength of the things that you're observing. Or if you want to think about it another way, if your detector is long enough, the photon doesn't bounce that many times in a gravitational wave cycle. And that results pretty much in a degradation of your sensitivity at that specific frequency. Now, this also happens in LIGO, by the way, but this feature goes like 1 over the length. So in LIGO, this feature is a 30 kilohertz, which is entirely irrelevant because LIGO sensitivity by then, it's really, really bad anyways, right? And so this is the short answer, is that this depends on the length of your detector, and the longer you make your detector, the lower this goes in frequency. And that's why the 20-kilometer detector doesn't show this feature. It's just that they have it, but it's a factor of 2 higher in frequency. So is above the region where it may be a nuisance for neutron star science, pretty much. I hope this. I'm sure if you ask an instrument scientist, they will give you a much more thorough answer, but this is the idea, is the free spectral range of the detector.
Okay, thank you.
No worries. I should also say, before someone asks, that the C20 has a dashed and a non-dashed version. That it's because some of this configuration can be tuned by changing the way mirrors and cavities work to have more of a broadband but slightly worse sensitivity, or a better sensitivity but in a slightly narrower band. So these are kind of options that are being considered too. All right. So what can we do with this type of observatories? Well, we can do a lot, and somehow I've already been talking for 20 minutes, unbelievable. In the project, we have come up with this like donut plot that somehow in a very pictorial and flashy way summarize the three main avenues of research you can do with Cosmic Explorer and Einstein Telescope. So in blue, you have extreme gravity and fundamental physics, and that means anything from modified gravity to looking for dark matter, for axion clouds, and so on and so forth. In green, we have studying dynamic of dense matter and extreme environment. So this means a neutron star equational state, possible QCD phase transition, cold and hot equational state, kilonovae, and so on and so forth. And in orange, we have studying black holes and also neutron stars, I should say, throughout cosmic history. That's what I'm going to focus a bit more later, because it's what I spend most of my time thinking about. However, before I go there and talk about what you can do with these hundreds of thousands of black holes that you will detect, I also want to stress again that some of those will be incredibly loud. And you can do the math. You will have dozens, sorry for the typo, dozens of sources per year that will have a signal-to-noise ratio higher than 1,000. For comparison, the loudest thing we found up to date had a signal-to-noise ratio of the order of 30. Okay, and having incredibly loud signal means that you can measure the parameter with an exquisite accuracy and precision, do tests of general relativity, so anything that requires you to be able to measure subtle feature, going after equational state constraints, and so on and so forth. To give you just one example, here I'm showing in this plot our measurement for the chirp mass, which is this combination of M1 and M2. So the orange curve is just the measurement for a simulated signal that looks like the very first gravitational wave we detected in 2015. So this is the uncertainty that LIGO saw back then. The blue vertical line is the truth, which I know because this is a simulated signal. And also you see in the vertical line the uncertainty that Cosmic Explorer would obtain. And you cannot really see it because it's just slightly thicker than the line at the true value. So I have to zoom in. This is the measurement that Cosmic Explorer would provide for the same signal. And I want you to notice the scale on the x-axis. This was, on the left-hand side, 7 solar masses. This is the order of 10 to the minus 2, 10 to the minus 3. So we are really talking of an incredible level of precision in the measurement and characterization of the loudest sources, of which we will have many per year. Now, on top of that, the thing which I found most exciting is that Cosmic Explorer will add another dimension. It will not just be more of the same or some of the same thing, but more precise, but will also open a new frontier, which is that of high redshift sources. This is shown in this plot here, where on the x-axis, I have the total source frame mass of a binary in solar masses. This assumes equal masses. On the vertical axis, I have redshift, so we are at 0. And what the various curves, colored curves show is for various detectors design, how far you will be able to see a source of any given total mass. So for example, this golden dash line is the mass of a neutron star binary. Advanced LIGO will see neutron star up to redshift of maybe 0.2. A sharp, which is the best you can do in 4 kilometers, and maybe 0.3, 0.4. Cosmic Explorer and Einstein Telescope would see them up to redshift of several. It's even more dramatic for binary black hole. This golden line gives you the mass of a binary black hole at the peak of the mass function, which is 10 solar masses. So the best you can do in the LIGO facility would be bringing you a redshift order of 2, the orange curve. Cosmic Explorer and Einstein Telescope will basically see black hole binaries farther than there should be stars in the universe, which is really, really something mind-blowing. This is also shown in a more dramatic way in this cartoon, where you see again on the x-axis the mass, here is on the top. On the y-axis redshift, again, we are at 0, 0 at the bottom. And these various lines show you the horizon of a Cosmic Explorer 40 for any given signal-to-noise ratio. So a signal-to-noise ratio of 1,000, you will be seeing things up to this gray curve. Signal-to-noise ratio of 100 up to this golden curve, and signal-to-noise ratio of 8 up to these cyan curves. And the various dots here and labels represent either some known sources for reference or some populations of binaries that we expect or suspect may be out there. And so, for example, you see the black holes and neutron stars that we are detecting right now in red and yellow and white. And you see that, we'll basically detect all of them. With Cosmic Explorer 40, they're all visible. And the thing that I found most exciting is that we may be going after populations of binaries, which right now would simply be invisible because they leave a high redshift, such as black holes left behind by population 3 stars, and if they exist, primordial black holes. So this is what I want to spend the last couple of minutes of my talk talking about before we move on to discussing everything. I should also say that here on the right side, you see the edge of the universe if you want. So Cosmic Explorer would be basically probing the universe in its infancy, when it was a few tens of million years old. Let me pause. Yes, Anna, go ahead.
Thank you. Just a quick question. So, at some point, the primordial black hole mass, of course, the higher the mass of the binaries, the lower the frequency in the rest frame. Yeah. And so you're up against that, right, with the redshift. So
absolutely.
Yeah.
Absolutely.
So I'm kind of wondering that purple region labeled primordial black holes, which are big ones, 100 solar masses or so. None of these experiments seem to get into that regime. Is that right?
I think that is absolutely correct. So what we have done here is to plot in with this, I guess, pink dots, a population of primordial black holes according to some theoretical models. And you're right, they are not all measurable or detectable exactly because of what you said, which I'm going to repeat in case people are not familiar with this idea. In our business, the higher the mass in the detector frame, the lower the frequency at which black holes merge. But when you bring a black hole farther and farther in a redshift, it gets a 1 + z boost in the mass. So if you make something very massive and very far away, it will basically redshift out of the band of your detector. And so this is captured by the curves here. And so you're exactly right. There is a range of mass redshift combinations where PBH would be detectable, and this is in the tens of solar masses. It could be 100 if they happen to be merging more locally than much more locally than where they're formed.
Very good.
If we are unlucky and they're all very massive and very far away, then yeah, we're not going to see them. We can only set constraints. I see another hand up by Jan.
Yeah, hi, quick question. So I'm not sure if I understand. Why are you not able to see PBHs that are much lighter, for example, 10 to the minus 10 solar masses or so?
Because the strain would be too small for LIGO, right? So
Okay.
the amplitude of the emitted gravitational wave signal depends on the chirp mass to some power. And and so, while formally they may emit gravitational waves in the band that LIGO is sensitive to, the amplitude would be too low. So if I go back to this plot, pretty much, they will be way, way down on the y-axis where we don't have sensitivity.
Okay. All right.
Unless, we are really lucky or unlucky and they happen to happen in the solar system. There's always, of course, a trade-off with the luminosity distance. But that's very unlucky.
They could be very close, right? If they're 100% dark matter, for example.
Yeah, so there is, you can do the math, and I'm sure there exists a combination of luminosity distance and mass where they might be not far from being detectable, then it's just a matter of, rates. How often would you expect something like that to happen?
Right. Okay. Thanks. Yeah.
Yeah, I see another end.
Yeah, my name's Craig Lindbergh. So sorry about the wrong name.
I can
And I'm not
only hear
really-
you very well, though. I don't know if it's just me. You're coming up very robotic.
Oh, really? Okay. Let me speak more slowly. I did put a couple of questions in the chat if you can't understand me. But I was curious about are there any plans for any detectors to go to higher frequencies? And I'm still, even though you partially answered this, I'm curious to know why what the nature of the restriction is on redshift, why you can only get certain redshift. I think you partially answered that, but I didn't completely get it. Sorry.
So I think I got both of the questions. All right, so yeah, let me start with high frequency. The answer is yes. Somehow it did not make it in this particular plot, but there is a design being developed by our friends in Australia. It's called NEMO, like the cartoon, I guess. And that stands for like Neutron Star Explorer. I don't remember what the M and O are, multi-messenger observatory, maybe something like this. Now, what NEMO is, it's what you attain if you tell yourself, you know what, I don't care about low frequency, I don't care about in spirals, I only want to learn as much as possible, from the merger of neutron stars. In that case, what you would care about is the region between 1, and a few kilohertz. And so what the NEMO design is basically getting rid of all of the fancy and expensive things that you need to improve the sensitivity in the low frequency where they don't care about, in order to save money and build something cheaper that give you a sensitivity comparable to Cosmic Explorer and the Einstein telescope in this region. Okay, so after I go out from full screen, I'm happy to put a reference on the chat if people are interested. So our friends in Australia, ANU and Monash and Perth are working on that idea. It would be much cheaper for Cosmic Explorer. By the way, apparently went away from my slides, but we are talking about the order of $1 billion to build one Cosmic Explorer or one Einstein telescope. NEMO would be something much cheaper. It would be on the order of tens to hundreds of millions of dollars. So same scale as LIGO or even a bit cheaper, but they would only be sensitive here, after which the sensitivity would basically explode. So they still rely on the existence of other detectors that tell them something is merging now, because by themselves, they may not be able to know that because they would miss the spiral, it would be buried in their noise. Now, to your second question about redshift. So the idea why these curves looks like the way they do, where they first go up and then go down, it's again, based on the fact that, on two facts. One is that when you have these two gravitational wave, these two compact objects merging, they will collide at some characteristic frequency, okay? After which, basically, after a few cycles after that, the gravitational wave is gone forever. So you really want to be sensitive at least up to that peak frequency corresponding to the merger. It turns out that the frequency at which that collision happens decreases like 1/m. So a black hole of a binary of 60 solar masses would merge at around 250 Hertz. If you make it 10 times more massive, it would merge at 25 Hertz. Okay, so that's one fact. The other fact is that if I take the same binary and I bring it a factor of 10 farther away in redshift, it will look in our detector like if it is a factor of 10-ish heavier. So the mass that we measure here at Earth are boosted by a factor of 1 plus z. But because more massive means merging earlier, that implies that, as your mass increase, at the beginning you win, because more mass is more charge, which means more amplitude, so more gravitational waves. But as you make it more and more massive, at some point you start being pushed out of band, and so the sensitivity goes down again. So that's why these curves go first up and then go down. I hope this helps. I'm happy to go through this, again later if people are curious, or now.
Salvo, there is a question.
Planning to. I did hear.
I didn't get anything of that, sorry.
I'm also not getting. Can you write your question? We are not hearing anything. I think the question should be also what are the Japanese planning, if anything?
Right. So thank you. Yeah, but I'm not seeing the chat, so thank you for letting me know. So right now, the Japanese don't have any plans that I know of for next generation detectors. A few slides ago, I had a summary of their plan for the next few years. So there is, of course, a gravitational detector in Japan called Kagra. It's in the same mine where the Kamiokande experiment is hosted. Now, they have run with LIGO in Virgo for short stretches of time in 03, you can see it here, and in the first part of 04. Unfortunately, they are far from the sensitivity where they originally were hoping to be. So you can see that, for example, in 04A, while LIGO was 150 megaparsec for neutron star, Kagra was at the order of a few megaparsec. And the main reason is that they have hit a lot of technical issues because they are pioneering basically a lot of technology that was not used in LIGO nor Virgo. For example, cryogenics. And, I'm not an instrument person. For me, it seems trivial, just turn the thermometer down and cryogenic. But it turns out that if you want to go cryogenic, you have to change the mirror because the coating of the mirror doesn't work at that temperature, the one that LIGO and Virgo use. But if you change the coating of the mirror, you have to change the frequency of the laser that you use. Anyhow, so there is a cascade of things that they were really the first ever to try. And a lot of these things have shown to be much more challenging than people feared. And so they're a bit behind. So, I think right now, most of their efforts are focusing in having Kagra join later 04 or 05 at a good sensitivity. And I'm not aware of plans farther in the future. All right, I hope this answers the question. Of course, also, even though it's not shown here, I should mention that there is also a LIGO being built in India called LIGO India, which, if everything goes well, may be operational for part of 05. So it could join the network then, and it should have the same sensitivity that LIGO will have. It's being built as we speak, pretty much. Okay, very good. Let me try to remember. Was there anything else, Anupam?
There is one more question in the chat from Mark Elwich. He's asking about what frequencies is the future LISA space-based detector going to be most sensitive to?
Okay, so right, thank you. We are talking on much lower frequencies. So if this is my plot and this is LIGO, they will be somewhere on the top left of my slide. So they will be, below the millihertz region. So millihertz is already where it starts being pretty bad. So it's 10 to the minus 4, 5, 6 hertz. That's where they're most sensitive. And so again, because of what I said earlier, more mass means lower frequency. So that tells you that LISA will be sensitive to supermassive black holes, mergers, because those merge at lower frequency than the stellar mass black hole that LIGO is sensitive to. So that's, microhertz region. And even lower than that, you have the pulsar timing array that, as you may have heard, has detected hint of a stochastic gravitational wave background a few months ago in the summer. And I should say, again, I'm not into do a 4 p.m., so I'm happy to go for hours. But if people are curious, there are also ideas for high frequency gravitational wave detectors, high meaning megahertz, gigahertz, things based on, I'm not an expert, but more or less, I know the idea is based on mainly atom interferometry. And, you know, so this would be top table experiments. There is some idea for a possible mission in space. Those would mostly be after stochastic gravitational wave from inflation, axions, strings, or this kind of more exotic things. All right. Now, you let me know if there is anything else. Otherwise, I'll move on. Actually, I'm nearly done. I don't have much more because I wanted to leave time for questions, which I'm very happy are coming. So as I said, I want to talk a bit more about population 3 black holes and primordial black holes. But again, what I want to stress here is that at least for the type of black holes and neutron stars that we know are out there, so, you know, the ones left behind from population 1 and 2 stars, the one that astronomers are seeing, the stellar mass black holes, those would be basically these white clouds here. Cosmic Explorer would see nearly all of the mergers in the universe, which every time I think about it, it really drives me like really like be crazy. It's like the way I think about it, because if you think about it, this implies that in one generation of gravitational wave detectors, from LIGO to Cosmic Explorer, that's 2 generations, we would go from seeing the very first gravitational wave source ever in the history of humanity to basically see all of them. And so the way I think about this is like if the person after Galileo had built the James Webb Telescope, right? You go like in 20 years from, you know, seeing the first thing ever to see nearly all of it, which is really, really remarkable. Now, this said, the reason why I'm excited is because there may be things that we don't know about or we're not sure about, like this primordial black hole and POP3 stars. So let me start with population 3 black holes. The idea here is that those may be the black holes left behind by the very first generation of stars. We don't know a lot about the population 3 stars. What people think it's solid guess is that they were pretty big. This is shown in this cartoon here, where the first generation star is a very big blue thing at the bottom. They had never been directly observed, just because they did not live long enough. And we didn't have telescope that could see far enough in the universe. Even James Webb is not going to find is not going to directly image first generation stars. They may see indirect evidence for. And now, one of the main reasons why it would be great to know more about the first generation of stars is that the black holes they leave behind, which I'm going to call POP3s, the black holes, may be the so-called seeds that, through repeated mergers, created the supermassive black holes that we see today at the center of galaxies, pretty much. Well, not only today, we see them up to high redshift. Now, what we know about POP3 stars is mainly based on theory and some amount of population synthesis, numerical codes. So what seems like a very good guess is that the peak of the formation of black holes left behind by POP3 stars would happen at very large redshift, maybe 10, 20, depending on exactly on the theory. And this, as I mentioned earlier, it's a redshift which is way higher than what LIGO could possibly dream of reaching. So it's incredibly exciting that with Cosmic Explorer, we would be able to go after this type of objects. So something that we have done in my group over the last few years is to check how well exactly next generation detectors would be able to characterize the merger rate history of binary black holes up to redshift where there shouldn't be any local population anymore, but there could only be population 3 black holes. So this is shown in this plot. It's very busy, so I'm going to take a minute to explain what it's showing. So on the x-axis here, we have redshift. We are here at 0, and here we go up to 15. The 3 solid curves represents 3 theoretical distribution for the merger rate on the y-axis. That is basically number of black holes merger per unit time per unit volume. So these are three curves that come from theory behind formation of black hole binaries in globular clusters in orange, or in galactic fields like the Milky Way in blue, or population tree black holes in pink. And if you're curious, these are the theory papers that these three curves come from. They're based on population synthesis. So what we have done in some of these papers is to simulate our own universe where the black hole binaries we detect come from some mixtures of these three populations according to the true curves you see here. And so the total merger rate history of our black holes that we have simulated is the white solid line that you see here at the top. And the white dashed line and the gray bands corresponds to our median and 68 and 95% uncertainty measurement on the total merger rate based on 2 months of Cosmic Explorer and Einstein telescope time. So what this is telling you is that if out there is indeed a very high redshift, a subpopulations of black holes formed by these population tree stars, again, I should say to be clear, relating to the question I was asked before, these assume some mass range. If there are thousands of solar masses, we're not going to see them. Those are tens of solar masses. But if they are there at that mass range, in 2 months of data, basically, we're going to be able to measure the whole merger rate history of black holes all the way to Z of 15 and show uncontroversially that there is a peak at Z of 10 or 12 or whatever that it's or can only be due to population tree stars. So basically, this will be direct evidence for the existence of a high redshift population of pop tree stars. And again, this is based on 2 months of data only, which is really remarkable. I should also say this analysis is based on, just for those of you who like this kind of things is based on Gaussian processes. So there is no astrophysical modeling. We don't assume that we know how many populations there are or anything like that. However, if you are willing to put some more modeling in your data analysis, then you can do even a bit more than just measuring the total merger rate. You can try to disentangle the contribution of these three subpopulations. And what you can do is turn that measurement in a measurement of the abundance of population tree black holes. So this is shown in this plot. On the x-axis, I have the abundance of population tree black holes. 0 means there are no population tree black holes. 5 means there is 5% of them over the total, and so on and so forth. The y-axis is just the probability. That's a measurement. So the green curve shows you our measurements with 2 months of data for a simulated universe where there were no population tree black holes. They just did not exist. And indeed, after 2 months of data, we can measure that the probability peaks at 0%, and the upper limit at 95% probability, it's of the order of a few percent. Instead, if we simulate a universe where there are population tree black holes, in particular 2.7%, that's the blue curve, you can see that the measurement peaks at the true value, which is this thick white line, and the upper 95th percentile is of the order of 7 or 8%. So that's great. With a few months of data, if those things are out there in the right mass range, we're going to find them or set a very stringent upper limit if they're not there. Okay, last thing I want to say, if you're willing to be even more, extreme or adventurous, even farther, there may be primordial black holes. Those were theorized in the 60s. They are basically formed not from stars, but directly from the collapse of fluctuations very early in the history of the universe, as shown in this cartoon by ESA. So they will be formed really very, very shortly after the Big Bang. And now those are exciting for very many reasons, of course. A discovery would have cosmological implication, but also they're exciting because, as someone mentioned earlier, they could be a fraction of dark matter, right? And theory tells us that those primordial black holes, they can be formed, depending on the formation model, in binaries that would make them merge at even larger redshift than population tree black holes. Here we're typically talking of redshift of 20 and above. And so you can play the same game and show whether next generation detectors could find those objects and show that they are out there. So by now you are familiar with this type of plot. This is the same type of analysis. On the x-axis, we have the redshift. On the y-axis, the merger rate, so number of sources per unit time per unit volume. Here, notice that the scale of the x-axis is different. Now we go from order of 10 to 40 in redshift. This again is for a simulated universe where we have the population 3 black holes in pink that peak a redshift at around 12. And then we have a merger rate of primordial black hole in cyan. This comes from a theory paper by Vitale et al. The merger rate of primordial black hole has the characteristic that it actually increases as Z decreases. And so the questions we wanted to address in this type of analysis was, suppose that we do have primordial black hole out there and they have this type of, merger rate history. Would we be able to disentangle this scenario from a scenario where there is only astrophysical black holes, such that the merger rate first goes up and then goes down like the pink curve would do by itself? And the answer is yes. Here again, you see in white, the overall, so the sum of these two populations, the solid white is the truth, the dashed white is the median, and the gray curves are 68 and 95% probability. So this is based in 4 months of data, and with 4 months of data, again, if this plateau is there, we're gonna find it at Z of 30 or 40. If instead there is no primordial black holes in this mass range, I have a plot in this paper, I'm not showing it, we would find, as we should, that the merger rate goes down monotonically with redshift. Again, the plot I'm showing here, it's model independent. If you are willing to believe theory model, you can fold those in your analysis and, for example, produce plots like this. What this is showing, it's measurements on the fraction of dark matter as primordial black holes on the y-axis in units of 10 to the minus 4. In the literature, this is typically called FBBH. And on the y-axis, we have the true ratio between primordial black hole and population 3 stars that we have used in our simulation. So 0 means there were no primordial black holes. 1/2 means that we had 50-50 primordial black hole and population 3 stars, and anything in between. And the square is the true value, the black square. The violins with the white lines are our measurements with the 90% credible interval on the measurements of FPBH. And so, for example, if we happen to live in a universe where there are no primordial black hole in this mass range of tens of solar masses, after 4 months of data, we're going to be able to constrain FPBH to something of the order of 5, 10 to the minus 5, which will be a factor of 10 better than relevant constraints in the relevant mass range, typically coming from microlensing with the Rubin. If instead there is a small fraction of FPBH in primordial black hole, we're going to be measuring it with a pretty high level of precision. All right, I'm going to leave conclusions on slide, and I think we have some more time for questions. And sorry, this took a bit longer, but we had a lot of questions, throughout. Thank you very much for your attention. I should also say, I did some of this work. A lot of this work was done by my group, and I want to put them on screen because they are really great. Thank you.
Thank you, Salvo, for this very nice talk. There are already lots of questions. Are there any more questions left for us to ask for the audience? Please raise your hand.
I go back to conclusions meanwhile.
I don't see one. So can I ask you? Sorry, there is a hand from Sanjay. Sanjay, can you please unmute yourself?
Yeah, I have a question about finding, exotic objects, black holes in the neutron star mass range. So what is the forecast for, putting limits on what fraction of these objects below 2 solar masses cannot be classified as neutron stars? In other words, will we have tidal deformation measurements for some large fraction of the neutron star population to see if there are any unusual objects?
Yeah, thank you, Sanjay. That's a great question, and something, of course, is very close to all of our hearts, because we already been in that situation a couple of times where we detected something was 2.6 solar masses. What is it? And so there are several answers to that, Sanjay. One of them is that simply that the measurements of tides will be better because the signal-to-noise ratio is higher. And so, hopefully by then we will have some idea of the, what the tides should be for neutron stars. And, you can use that information with your next generation detections to check whether those objects are consistent with having non-zero tides, in which case they will be neutron stars, or some exotic, I guess, compact objects, or black holes. The other answer, though, Sanjay, which I think is probably more, is a safer bet, at least when it comes to distinguishing black holes from like light black holes from heavy neutron stars, as opposed to black holes from boson or Proctor stars. That's a whole different thing. Is that the sky localization will be much, much better. So if in Cosmic Explorer ET we detect something like, for those of you who know what I'm talking about, like 1908-14, which was this object that, this binary, that 2.6 solar mass object that we don't know if it was the lightest black hole ever or the heaviest neutron star ever. Well, if you localize that to a sky location, better than a square degree, you can throw all the telescope time that you want and look for a counterpart that would tell you, whether a neutron star, or could tell you at least whether a neutron star was involved. So I think these are probably the two main avenues that make me optimistic. More information about tides and component masses too, I should say, and the fact that more of those will come with a sky location such that if you did not see anything, you can be pretty confident there was nothing to see, because it's a very small patch in the sky, as opposed to now, when if you don't see anything, well, who knows? It was 300 square degrees, maybe I just missed it, right?
Right.
And so those are, I think, the main two things. There are other things that you can do, but that's why I am optimistic. Then, of course, Sanjay, there's always going to be events for which you just don't have enough information. That's still going to be the case. If you put something at Z of 5 or 4, tides will still be uncertain, But for anything at 0.1, 0.2, they should be measured pretty well.
All right, thanks.
There is one more question in the chat. Maybe I can read that out. So this question is, will the future generation gravitational wave detector allow one to distinguish between a neutron star and a hypothetical quark star by exploring the equation of state? Yeah, so that's related to basically what we're talking about. The answer is, let me see. There are two parts to this answer. I want to say that the jury is still partially out. However, and I'll explain why in a second. However, the data we have as of now in terms of like publications, including actually by people at Berkeley involved with this effort, is that that may be done exactly because if you have something with a signal-to-noise ratio of 1,000, and you have a lot of information that you can follow through in this spiral, and the reason why I didn't say that is certainly going to be happening is because all of these studies assume that we have some information about the waveform evolution of such object. Okay, so to the extent that we believe that our understanding of the neutron star or exotic neutron star waveform evolution in the Leighton spiral, it's reliable, then it seems like it can be done. The question is, do we actually have under control those simulations well enough to trust those results, right? And those are, as probably many of you know, they're incredibly hard numerical relativity simulations to perform, because every time you have matter, things become much more complicated, even if it's not exotic matter, even just normal matter, right?
But that's actually the perfect cue for me, to actually advertise a program that we're going to have at the INT. And at Sanjay and Sophia was online. Sophia was online earlier. Is also involved about the question of state measurements with next generation detectors. One of the questions that will happen in late August of this year is one of the questions is indeed, do we have enough information from the theory? Do we have enough information from the waveform side? And so on and so forth. Basically, everything that could limit the sensitivity of the detector, right? Because the idea being that if you build something that is worth $1 billion and could measure the radius of neutron star to 100 meters, you don't want to be limited by your waveform at 1 kilometer,
Yep. Thanks, Salvo, for this very nice seminar. I don't think there are any more questions. Thank you for giving the seminar. And
thank you very much for having me. And thank you for all
Okay.
the questions. That was really
Okay.
useful.
Okay.
Bye, everyone.
Okay. Bye. So we'll see each other next week. Yep.
Oh, Sophia's still there. Okay, very good. So if you have questions, she's a good person to talk to, and so is Sanjay about this INT program. All right. Bye, everyone.
Bye.
The rest of the day.